Hello, the topic for this lesson is the Gram-Schmidt process. So let's begin with a brief overview of the lesson. So in the previous lesson, we talked about the orthogonal projection of a vector along a subspace. So here's a vector y, for example, and here's subspace W. You want to project y onto W. So that's the projection, and then that's the residual vector z equal to y minus projection. Now, the orthogonal projection actually relies on knowing an orthogonal or orthonormal basis for subspace. So in this lesson, we'll talk about how you can actually construct such an orthogonal or orthonormal basis starting from an arbitrary base for a subspace. And this process is called the Gram-Schmidt process. And in fact, it relies on using orthogonal projections. Now, once we've done that, we can talk about the QR factorization for an invertible square matrix, a very important concept in linear algebra. Okay, so let's begin with a motivating example. So here is a pair of vectors x1 and x2. And if you take a dot product, you see the dot product is not 0, it's 75. So what you can do is you can first of all define a vector v1, which is x1, then work out the projection of the second vector along v1, and then subtract it off. And now the two new vectors v1 and v2 are actually orthogonal. So that's the idea behind what is called the Gram-Schmidt process. So suppose you have a set of p linearly independent generators for a non-zero subspace W of Rn. So p could be anywhere between 1 and n. So of course, this set is then called a basis for W. What you can then do is, starting from here, you can define new vectors by taking the first vector v1 to be x1, just like we did early on, the vector v to be the vector x2 minus the projection of x2 along v1, just like early on, and you keep on doing that, and very soon you will have an orthogonal basis for the subspace W. Now, of course, once you have the orthogonal basis, you can convert to an orthonormal basis by simply dividing each vector with its norm. Okay, so let's take an example of that. So here you have a set of vectors x1, x2, and x3 in 3 space. Let's check they are linearly independent. That's the independence condition, but you see they are not necessarily orthogonal. So what you do is begin by defining v1 to be x1, v2 to be x2 minus the projection of first vector on x1, etc., v3, and then if you check, you see that you actually have an orthogonal set. So that's a really simple idea. By using projections, we can start with a basis and obtain an orthogonal basis. Okay, so now we actually have a very nice function called the orthogonalized function in Wolfram language, which can do that for you automatically. And in fact, it does more. It gives you an orthonormal basis for a subspace by orthogonalizing the vectors in a set of generators, a basis. So for example, here you got 4 vectors in R4. Check they are linearly independent. Use orthogonalize the inbuilt function to actually get the basis, and check that the basis is actually orthonormal. So that just says that you have an orthogonal matrix, so you have an orthonormal basis. So this function is very useful for constructing these orthonormal bases. Okay, now one can talk about the so-called QR factorization. So if you have an invertible square matrix of order n, then the fact is that such a matrix is written as a product of an orthogonal matrix and an upper triangular matrix. So that's the A equal to QR relation over here. And the columns of Q, this Q over here, can be obtained by applying the Gram-Schmidt process to the columns of A treated as vectors. Of course, once you have the matrix Q, you can work out the matrix R by simply doing a Q transpose because you have an orthogonal matrix, so that's quite easy. So this can be done quite easily in the Wolfram language by using the QR decomposition function. Okay, so as an example for the QR decomposition, here's the matrix A. Let's work out the orthogonal factor Q by doing an orthogonalize, and you need to transpose over to get the columns in the right place. That's the matrix Q. Work out the matrix R with the same formula as early on, transpose of Q dot A, And now let's check that A is equal to Q dot R. So that's the kind of hand method for doing the calculation, but you can also use the QR decomposition function quite easily. So here is an invertible 3 by 3 matrix A. Its determinant is not 0. So you call the built-in function QR decomposition, and you get back two pieces. You get back a Q and an R. Now, the required matrix is actually the transpose of Q. And then you can work out the upper triangular matrix R by simply taking the second element of the pair over here, and you can now check that actually have A equal to Q dot R. So that's the end of this lesson. And the main point is that the Gram-Schmidt process can be used to construct an orthogonal or an orthonormal basis from a given base for a subspace W. And luckily, we have a very nice function called the orthogonalized function in the Wolfram language, which can do that for you automatically. Now, once you have that understood, then one can talk about the QR decomposition. So basically, you have an invertible square matrix to start with, and you can factor it into an orthogonal matrix Q and an upper triangular matrix R. And the built-in function QR decomposition can be used to do that automatically for you. So with all that, we are now ready to talk about the so-called least squares solutions for inconsistent linear systems in the next lesson. But for now, I'll stop. Thank you very much.